Welcome back. Our next task is to equip ourselves with some of the basics of propositional logic. Now, this is a course about inductive logic. So you might be wondering, why are we lingering in the territory of simple deductive logics? The reason for this is that deductive logic plays a crucial role in the inductive logics we'll be using throughout the course, and in particular in probability theory. And so before we proceed, we'll need to pick up the necessary portions of basic propositional logic that we'll employ moving forward. By the end of this lecture, you should be able to 1. Translate sentences from English into propositional logic. 2. Determine the truth conditions for logical propositions using truth tables, a method with which you will become acquainted, if you are not already. 3. Determine whether a proposition is tautological, contradictory, or contingent using these truth tables. And 4, finally, to determine whether an argument is valid using the truth table method again. The basic unit of analysis of propositional logic is the proposition, where a proposition is a sentence that makes a definite factual claim. An atomic proposition is the simplest such sentence, one that cannot be broken down further into other simpler propositions. Examples of atomic propositions include the die came up even. Los Angeles is a city in California. The atomic mass of carbon is 12 daltons. However, there are many expressions in the English language that we should recognize do not make definite factual claims, and so are not propositions. Non-examples of propositions include exclamations like "not the gumdrop buttons," imperatives like "execute order 66," and interrogatives like "to be or not to be." Composite propositions involve the assembly of atomic propositions using another kind of expression, logical expressions, such as and, or, and not. These 3 in particular will be the 3 logical expressions that we will equip ourselves with during this foray into propositional logic. We can consider examples of composite propositions like the die came up even and it did not come up too. Los Angeles is a city in California, or Shiraz is a province in Iran. The atomic mass of carbon is not 13 daltons. In propositional logic, we typically represent simple propositions, atomic propositions, with lowercase letters for convenience. By convention, we'll begin with P, Q, R, and so on, and we'll avail ourselves of other portions of the alphabet if we run out. Again, in the language of propositional logic, our symbolic notation for and, which we also call conjunction, will be this hat shape. And for or, which we also call disjunction, will be this wedge shape. And for not, which we also call negation, will be this bar shape. Let's do a few examples together in which we translate from English to the language of propositional logic. Consider the composite proposition, the patient has a cough and a fever. For our key, we will use C to denote the patient has a cough, and F to denote the patient has a fever. Our translation then becomes C and F. The patient has a cough, and the patient has a fever. Consider the patient has either a viral or a bacterial infection. For our key, we'll use V to denote the patient has a viral infection, and B to denote the patient has a bacterial infection. Our translation then will be B or V. The patient has a viral infection or the patient has a bacterial infection. Consider the patient does not have lupus. For our key, we'll use L to denote the patient has lupus. Our translation then yields not L. The patient does not have lupus. Consider something a little more complex. The patient has either heavy metal poisoning or porphyria, but not both. Or she might be having a severe allergic reaction. For our key, we'll let H be the patient has heavy metal poisoning, P the patient has porphyria, and A the patient is having a severe allergic reaction. For our translation, we get H or P, the patient has heavy metal poisoning or the patient has porphyria, and not H and P, right? And it's not that both the patient has heavy metal poisoning and she has porphyria, or the patient is having a severe allergic reaction, that is, or A. Notice that here, but is acting as it often does in English, in a way that is equivalent to and. With these preliminaries in place, we can now move to the truth table method. The truth table method allows us, among other things, to determine the truth conditions of composite propositions. Right? The more complex propositions that we get by combining simple atomic propositions with logical expressions like and, or, and not. The way that the truth table method accomplishes this is by producing a table that we divide in parts. On the right, we have the composite proposition that we wish to analyze, that is, whose truth conditions we want to determine. And on the left, we have a listing on the top row of all of the atomic propositions at play in the composite proposition of interest to the right. And in the columns on the left, the possible truth values that those atomic propositions can take. Here, in the case of negation, we can see that for the composite proposition not P, the only atomic proposition is P. And so we list the truth values of P in the left column, true and false. And now we can observe that this table actually here gives us the very meaning of negation. That is to say, we see that negation gives us that not P is false whenever P is true, and true whenever P is false. Turning to conjunction, what we see is that P and Q is true when P is true and Q is true, and false otherwise. Notice now that because we have two atomic propositions, P and Q, rather than merely one, there are four logical possibilities for the combinations of truth values that each P and Q can take. We'll see later the more general pattern of how to produce and account for the logical possibilities involved with many atomic propositions. For now, perhaps you can even think on your own about what is the logic underneath the number of logical possibilities in relation to the number of atomic propositions. But let's move on. For disjunction, we see that we get that P or Q is true in all cases except for when both P is false and Q is false. In other words, P or Q is false when P is false and Q is false, and true otherwise. Importantly, this is a specific version of the English OR, which we sometimes call the inclusive OR, to distinguish it from another version, the exclusive OR. The difference between these two versions of OR that we can use in everyday language is that an inclusive OR allows either P or Q to be true, and additionally, the proposition will be true if both of them happen to be true. So this is something like, Margaret went to the bazaar, or Nima went to the bazaar. And it would be also fine if both went to the bazaar. However, sometimes we mean, and this is often clear from context, that either Margaret went to the bazaar or Nima went to the bazaar, but not both. That is the exclusive OR, and we're not using that here. As you can see from the truth table, P or Q is true when either P or Q is true, and when both P and Q are true. Good. Now we'll consider a method for determining the truth conditions of yet more complex composite propositions that can be made up of many atomic propositions and many logical expressions, combining them. The general approach is basically to solve the truth values of the logical expressions piece by piece. Here we can start with not P and simply invert the values for P underneath it. And then we can plug in the known truth values for Q and recall that an OR statement is true just in case either of its disjuncts is true, meaning it's only false when both of its disjuncts are false. And from that we can determine the truth conditions of the entire composite proposition, not P or Q. Notice that this is a contingent proposition, which means that it is a proposition that can be true or false depending on the truth and falsity of the atomic propositions that compose it. And what that means is there are some conditions under which it can be true, and there are some conditions under which it can be false. All of the propositions that we've dealt with so far have had this property. They have all been contingent propositions. However, contingent propositions are not the only sort of proposition. Here we see the proposition P or not P, which when we plug in the values for P and the truth values for not P, and recall that OR is only false when both disjuncts are false, we notice that this proposition is never false and always true. And this property of being always true makes a proposition a tautology or tautological. This is an important class of proposition. And indeed, I'd invite you to think about why it is in this context that a proposition of the form P or not P must be a tautology. You can begin plugging in statements like the door is open or the door is not open. And notice that for many cases, that indeed exhausts the space of logical possibility. Our next proposition is P and not P. And when we plug in the values of P and not P, and then consider the character of and, which is true only if both conjuncts are true, we notice that this proposition is always false and never true. This is called a contradiction. That is to say, more generally, any proposition that has the property of being always false is considered a contradiction or a self-contradictory proposition. This too is an important class of proposition. And again, I'd invite you to think through why such a proposition might be considered contradictory, and plug in for P things like the person is alive and the person is not alive, right? The door is open and the door is not open, and so on. We can consider one somewhat more sophisticated case with 3 atomic propositions in order to get ourselves used to thinking with just a few more variables. And notice that the same precise pattern applies. We first determine the truth values of P and Q and remind ourselves of how AND works, which is that the proposition is true when both P and Q are true and nowhere else, which yields this darker gray column of truth values. Now considering the proposition R, we plug in its truth values and recognize that we have to combine that with the whole proposition P and Q under the logical expression OR, which we recall is false only when both disjuncts are false. We get the truth conditions for our contingent proposition with 3 atomic propositions as constituents. We can now return to the concept of validity and examine it from the perspective of truth tables. Recall that an argument is valid when the truth of its premises guarantees the truth of its conclusion. This can be determined now via our truth table method. Let's consider the argument P or Q, not P, therefore Q. For those of you interested, this pattern of argument is called disjunctive syllogism. Let's translate it to the truth table method. Our translation proceeds as follows. Just as before, we have the logical atoms in the far left of our truth table, but now we can divide up one portion for the composite propositions or atomic propositions that make up our premises, and another portion of the table for our conclusion. And in particular, the test that we need to run for validity is it the case that whenever the premises are all true, is the conclusion also true? And here we can see, indeed, when P or Q is true, and when not P is true. This is the third row of our truth table. Q is also true. And so the argument that goes from P or Q and not P to Q as its conclusion is indeed valid, because wherever its premises are true, its conclusion is true. For completeness, let's consider a case of an invalid argument and use the truth table method to see how it is invalid. Here we have the argument P or Q, and P, therefore not Q. Notice that there are two cases where all of the premises of this argument are true. One where both P and Q are true, and one where P is true and Q is false. In the latter case, shown in the second row, it's in fact correct that when the premises are true, the conclusion, not Q, is also true. However, in the first case where both the premises are true, that is, where both P and Q are true, we notice that not Q is false. And so it is not the case that the truth of the premises guarantees the truth of the conclusion, and this argument is not valid. And this can be seen easily using the truth table method. Now, you're going to be making a number of truth tables, so it can be helpful to have a technique for producing truth tables, especially when you are dealing with 3 or more propositions. And this is a technique that you'll be able to apply more generally anytime you have Boolean or two valued variables whose combinations you want to be able to efficiently list. The general technique is as follows. You'll know that you're going to have 2 to the k rows because there will be 2 to the number of atomic proposition combinations that you need to account for. And the way you can think of how that is true is that each proposition can have one of 2 values. And imagine a branching structure in which the first proposition can have the values either true and false. Now consider that at the next node, it can have the next proposition can have the values 2 true and false, and so on. So you get a multiplying of 2 times 2 times 2 to the number of propositions that you have. So if we have one proposition, we get 2 to the 1, or 2 combinations to consider. 2 propositions, we get 2 to the 2, or 4 combinations to consider. 3, we get 8. 4, we get 16. 5, 32, and so on. Now, the way to build the truth table, or one way to do it rather efficiently, is simply take the first atomic proposition, here P, and make the first half of its values true and the second half false. And for the next proposition, make the first half of that first half true and the second half false. And again, similarly, make the first half of the second half true and the second half of the second half false. And repeat this by subdividing the number of propositions. So if we only had 3 variables here, right, we would know that we'd have to have 8 combinations. So under P, we would need 4 truths, right, and 4 falses. And then under Q, we know that we'd have to have 2 truths followed by 2 falses, followed by 2 truths, followed by 2 falses. And under R, we would have a true followed by a false, repeated 4 times. But even if we had, imagine, 5 atomic propositions, yielding 32 truth and false, 32 logical combinations of the 5 propositions. Then we know that we would need to take for our first letter 16 truth values and 16 false values, and for our second letter we would need 8 true, 8 false, 8 true, 8 false, and so on, and to continue to apply the same pattern. And to look at this concretely, for the case of 3 propositions, notice that we do just that. 4 truth values, followed by 4 false values, followed by 2 true, 2 false, 2 true, 2 false, 1 true, 1 false, and so on. Hopefully, this will make your truth table making more efficient, and you will get to use this technique in the future wherever you have to deal with listing the possible combinations of multiple Boolean valued variables. Thank you so much for joining me, and I look forward to diving deeper with you into inductive logic next time. Be well.